Welcome to another edition of Math for Note. In this edition, we'll prove this identity, which is we are looking at the sum from k is equal to 0 to n of n ck squares, and if we sum it all, we will get 2n cn. Now, we know that n ck is n factorial by k factorial into n minus k factorial. This is the number of ways of choosing k objects from n distinct objects. We will be using this combinatorial notion to prove this identity. Now, what is 2n cn? Now, this is the number of ways of choosing n objects from 2n distinct objects. Now, let us divide these 2n items into two groups. So, the first group consisting of n objects. So let's call this group 1, and we have another group of objects numbered n plus 1 to 2n, and this we call group 2. Observe that any choice of n distinct objects from these 2n distinct objects will consist of k objects from here and n minus k objects from here. That is, there will be k objects from group 1 and n minus k objects from group 2. And k can vary from 0 to n. Now, once we observe this fact that there will be k objects from group 1 and n minus k objects from group 2, then we know that the number of ways of choosing k objects from group 1 and n minus k objects from group 2 is nck into ncn minus k. And since the k varies from 0 to n, we have n plus 1 cases. The first case being when k is 0, the second case is when k is 1, and the n plus 1th case is that when k is n. So we see that the total number of ways of choosing n objects from these 2n distinct objects is k is equal to 0 to n nck into ncn minus k. So what we have got is that 2n cn is summation of k is equal to 0 to n nck into ncn minus k. But from this formula we see that ncn minus k is same as nck. So therefore, we have nck into nck, which is the result to be proved. Now, this is a special case of a more general identity, which is as follows. So the identity is called Vandermonde identity. The Vandermonde identity states that if you have positive integers m1, n2, n, then sum over k is equal to 0 to n, m1 ck into m2 cn minus k is equal to m1 plus m2 cn. The proof is exactly similar as before. We break up into two groups. So group 1 consists of m1 distinct objects, and group 2 consists of n2 distinct objects. So summation k is equal to 0 to n m1 ck into m2 cn minus k is the number of ways of choosing n objects out of m1 plus n2 distinct objects, which is the right hand side, which is m1 plus m2 cn. It may be noted here that if in nck, if k is greater than n, then we treat that as 0. So if we have RCP, this is equal to 0 whenever p is greater than r or p is less than 0. So this is the convention that we use here, and using that convention we get this identity. Thank you.